Hi, my name is Wang. Today I'm going to talk about my final project, which is to build a classifier to detect the checkback in multi-party conversations. A little bit of the background here. The checkback is one of the phase in closed-loop communication. The closed-loop communication is a type of communication during the high-stake crisis situations. So in those kind of situations, miscommunication is a common cause of adverse events. So closed-loop communication has been recommended in team research literatures as a communication behavior that can guarantee the accuracy of information exchange. So usually people in surgeries like medical scenes, military scenes, or search and rescue, those kind of scenarios, they will be trained to use the closed loop communication. And then the checkback is a very essential part of the closed loop communication. See, example would be someone we'll call the sender. Sender will initiate a message, and this phase is called the call out. For example, green is a role, is a member of the team. Say he said, "This is green. I'm finishing this side. Blue, could you check the central?" And then the other role or the other member of the group will respond to this initiate. Blue will say like, "This is blue. Okay, I'll go check the central." We can see that check and central are actually some main information of the initial message or the call out session. So usually check back is a kind of respond, and usually by paraphrasing or repeat the main information of the call out message. And finally, the sender will verify the message, and this phase called closed loop. For example, green may say, "Thank you, blue," to verify the checkback. So the objective of my project is to build a classifier that could detect the important phase, the checkback phase in the multi-party conversations. So basically, this is a natural language processing project. Okay, so the data set I use is collected from a simulated urban search and rescue game. This game is developed by a team that they are doing the research to investigate the successful team behaviors in urban search and rescue scenarios. And then the data set include 64 teams performed 127 trials in total, and then they produced this many utterances in total. So this is a screenshot of the manager's view, the master's view of the game. So this is one player, this is another player, and then this is a third player. So they have each have a role. Perhaps the right one is the medical specialist, and then the blue one could be engineer to move large rubbles from the way. And then the last one perhaps is someone with a stretcher that could move the victims from the scene. So the data is a recording of their cooperation in the game. So I did some data pre-processing before I implement the model. First is to find the sentence pairs, because the transcript that we have is something like here we have perhaps team and then we have a trial, and we have a timestamp, and then we have role and utterances. But actually, we need to use the sentence pairs, like the callback, call out, and check back. So the first thing I do is to, like, in 5-sentence level, 1, 2, 3, 4, 5, 5-sentence level, and then find the pairs. So one cannot check back with themselves. So if the first utterances is A, we're going to say here B is a different role. B perhaps checking back for A, and then C checking back for A. So here in this 5 utterance window, we can find 2 pairs. And then we move to the next 5 utterance window. The initiate also is A, and then can use B. Here we have C again, and B. And then move to the next window. Oh, sorry, next window is here. You can see, although we have some repeated sentences appear, but the pairs are unique. A only go with B and C, and then we move to the next one. The next one only go with B, C, and not going back. So that's how I detect the pairs in the transcript. So this is the pairs. This is the result of pairing. Finally, I got 35,000 some pairs in total, and then formatted like sentence A as the initiate, and then sentence B is the potential checkback. Okay. So I got a sentence A and sentence B. I still need to further inspect the data to find some patterns or some trends before I can decide which kind of model I would like to use. I use a concept called cosine similarity. To find the cosine similarity, we need first the word vectors. So in natural language processing, we cannot directly ask the computer to precise the word, the strings, the characters. We have to transform the word into numbers that the computer can comprehend. So one way is word vectors. What is word vectors? So here is a 2D example. Although in real situation, you can never see a word has a 2D vector. But right now, let's say apple has a vector, perhaps 1 and 5, 6. And banana perhaps have a vector of 1.5 and something like 5. And automobile has a vector of something like 6 and 1.5. And then those vectors are defined by the context of the word appears in the corpus. For example, apple and banana always appear together or usually appear in the same piece of text. Then they are given similar word vectors. But for automobile, it rarely appears at the same text or context with apple and banana, so it will give a very different word vector. In real situation, the word vector has many dimensions. For example, the one that I used called glove 6B50D something has 150 dimensions for each word. So here are the words. All of the numbers behind that is the word vector. Okay. So using those word vectors, I can compute the similarities between words and also between sentences. So because the angle between the vector apple and the vector banana is less than the angle between apple and an automobile, the cosine of this angle between apple and banana would be larger or greater than apple and automobile. So we can just compute the cosine similarity with this formula. It's the dot product of vector A and vector B divided by the length of vector A and the length of vector B. So here are the results that I got from the cosine similarity. We can observe from the cosine similarity and from the data that the data is highly unbalanced, with a very large proportion of pairs are not checked back. They are actually unrelated sentences. Only very few of them are checkbacks. And then the cosine similarity between pairs are skewed to high values rather than low values. We can see from this row here, a lot of the cosine similarities are very high, below 0.7. And then only a few of them are below 0. Actually, so my first thought I would like to do, oh, I have to clear this. Okay, so first I would like to do something unsupervised way of classify to do the classifier. I would like to say like one class SVM to find, because I think because we have very rare instance of checkback, so the checkbacks could be an outlier. So that we can use some outlier detection methods to find the checkbacks. But I was wrong, actually. So this is the distribution of the cosine similarities. We can see the rare situations are actually very low cosine similarities. And then the high cosine similarities are very kind of centered, dense here. And then this is a dense plot of the distribution of cosine similarity. We can see the most dense part is somewhere at perhaps 0.98 or let's say 0.8, 0.89, 0.85 something. So that makes unsupervised way very hard or impossible. So I have to annotate my data. But there are 35,000-ish data sets. I have no time, and that is so time consuming to annotate all of them. So I use this few shot learning and human in the loop approach. What does that mean? So you can manually annotate a small part of the data. In my case, 2,000 pairs out of all of these pairs. And then I can train the model, just use the 2000 pairs, and then test the F1 accuracy of the model, and then make predictions on a new set of unlabeled data. This new set of unlabeled data are extracted from the large corpus minus the 2000 pairs that are already labeled. So the predictions will be annotated again, annotated the data, and then give a F1 and accuracy of the prediction, and then loop the newly labeled data and train the model again. So basically go to here, train the model here, and then repeat 3 to 5. For several rounds until we have a reasonable F1 and accuracy of the model. And then, of course, the F1 and accuracy are tested on the new data set. Okay. So the method I finally adopted is logistic regression. And then the features I used is all of the sentences, vector count. So the package scalar in Python can convert all of the words in the sentence A and sentence B. So sentence A has a set of features, sentence B has a set of features. So altogether, and all of the sentences, there are 5,000 dimensions, and then also the cosine similarity can also be combined together as the features. So finally, oh, by the way, of course, this is a binary question. So in the initiate labels, I found 63 positive and nearly, I think nearly 96% of the negative. So that means without using the model, if we give all of the instance a negative label, we will have a 96 nearly percentage of accuracy. So this is the result. The first round of the model predicted on your data site got an F1 score pretty low. We can say there are very few true positive instances and a lot of false positive and false negative instances. So the accuracy is not so much better than purely give negative labels to all the data set, to the entire data set. So that is not a very good model. And then when we loop in human label at the second round, I got a hair F1 score, hair true positive, still 4 plus 7, still not so good, but I got an accuracy of 98. Actually, compared to the very base level of 97, that is not so much an improvement, but still is something improvement. So finally, I got to the third round. The third round gives true positive, very much to all of the true positive, and not all of them, but a lot of all of the true positive, and then just 3 false negative. And then the accuracy, well, that's strange. The accuracy actually decreased a little bit, but has a very high F1 score than before. Finally, some discussion here for the classifier that I built, the imbalance of the label makes the accuracy pretty high, but that doesn't mean the label is highly confident when making predictions on new data set. The human-in-loop approach did improve the performance of the classifier to an acceptable level of accuracy and F1 score, which is F1 93 and accuracy 98. Okay, that's my project. Thank you very much for listening, and I appreciate any suggestions and feedback. Thank you very much.